All right, welcome everyone. Thanks for joining. Today's speaker is Dr. Bharat Kunduri, and he's a research assistant professor in the Electrical and Computer Engineering Department at Virginia Tech. And prior to joining Virginia Tech as a research faculty, he worked in industry as a data scientist. And since 2016, he has been a part of several studies analyzing the dynamics of plasma convection in the inner magnetosphere, Sub Auroral Ionosphere region. His research interests also include developing machine learning models for predicting space weather phenomena such as the Falkland current system. And today he will present a talk titled Large-Scale Observations and Empirical Modeling of the Sub Auroral Polarization Stream. So go ahead, Bharat.
Thank you, Nick. Thanks for giving me an opportunity to present today. I really look forward to some feedback from you folks. So hi, everyone. My name is Bharat Kunduri. I'm a research faculty at Virginia Tech. I work for the Virginia Tech SuperDAN group. The focus of my talk today is the Sub Auroral Polarization Stream, mostly centered around observations made by the US mid-latitude SuperDAN chain. I'll begin with an introduction to Sub Auroral Polarization Streams and the SuperDAN radar network, and then move on to some of the observations that we made with the mid-latitude SuperDAN radars. So what are SAPs? SAPs are Sub Auroral Polarization Streams. So if you look at the Sub Auroral Ionosphere during nighttime, typically, plasma flows are very slow. They range a few tens of meters per second whenever there is no strong geomagnetic activity. During quiet times, you would probably see plasma flows in the 10 to 70 to 80 meter per second range. But generally, during disturbed geomagnetic conditions, especially when there is a geomagnetic storm, you see features, high-speed plasma flow features called SAPs, or Sub Auroral Polarization Streams. These are westward-directed flows. They range a few hundred meters per second and sometimes can reach a few kilometers per second. I think more recently, people have been talking about flows reaching more than 5 to 10 kilometers per second. But anyways, in the interest of in this study, I'm going to mostly focus on flows between a few hundred meters per second to 2 kilometers per second, which is the resolution limit of SuperDAN radars. Historically, SAPs were analyzed using measurements from low Earth orbiting satellites like the Atomic Explorer. DMSP has made several tremendous contributions to SAP studies. Actually, a couple of examples are shown here. This is from a DMSP F-13 satellite, and there's also measurements from incoherent scatter radars, especially the Millstone Hill incoherent scatter radar. Like any study, it's an introduction to SAPs is never complete without this standard picture from Foster and Vo 2002 paper. This picture presents SAPs measurements from two different instruments. The top instrument is from the Millstone Hill incoherent scatter radar. You can see a longitudinal profile cut of plasma convection and electron densities. So SAPs are located below the auroral oval region. They are reaching a velocity of about 1.5 kilometers per second in this region. The peak velocity is about 1.5 kilometers per second, and the broader velocity is ranging a few hundred meters per second. Poleward of this is what you see is the standard two-cell convection pattern that's located inside the auroral oval. Another feature that you can see from this plot is that SAPs are co-located with the mid-latitude density trough, which is depletion in the electron densities in the mid-latitude or the subauroral region. The same event is observed in the DMSP F-13 satellite. The top two panels present electron and ion flux, respectively. The auroral oval is, this is predominantly on the night side. The auroral oval is about located at around 59 degrees. And equatorward of the auroral oval, you can see enhanced plasma convection reaching almost 1500 meters per second. This is the SAPS region, and poleward of it is what you call the two-cell convection pattern. It's also directed westwards. So in summary, SAPs are high-speed westward flows that are located below the auroral oval in the dusk-midnight sector. So what's producing these high-speed or subauroral flows that are distinct from the two-cell convection pattern, right? So I would divide that into two separate components. One is a magnetospheric contribution, and another is the ionospheric contribution. The magnetospheric contribution is expected to be coming from two factors. One is a separation between the ion and electron precipitation boundaries in the night side. So during strong geomagnetic disturbances, the ion precipitation, the equator ion precipitation boundary is expected to move earthward compared to the equator electron precipitation boundary, resulting in the generation of a poleward directed electric field. And when you map this into the ionosphere, resulting in a radial electric field in the magnetosphere. And when you map this into the ionosphere, it maps as a poleward directed electric field, resulting in a westward E cross B drift. Similarly, the strong plasma pressure gradients in the ring current can drive region 2 field aligned currents. And when these region 2 field aligned currents are flowing into the low density trough region, what happens is there is hindrance to current closures with the region 1 field aligned current system, and as a result, strong poleward electric fields are set up. And this results in a westward directed Saps flow with E cross B drifts. So that's the magnetospheric component. And I'm talking about the traditional paradigm of Saps generation here, which was developed starting from 1990s all the way to early 2000s. So the other component is the ionospheric feedback component. So since Saps are located inside the mid-latitude density trough, and especially when the electric fields exceed 50 millivolts per meter roughly, it is expected that they lead to an increase in the recombination rates, and as a result, you would see a decrease in the density of the trough. So, which further creates an increase in the electric field, and a positive feedback loop is set up, increasing the electric fields, and which further reduce the density of the trough. So, Saps are one of those unique features where there is an active ionosphere-thermosphere system contribution in plasma convection, at least at the sub-auroral latitudes. So that's the traditional paradigm. More recently, several newer insights into Saps have been developed. I'm going to present one of those studies. This is by Dr. Evgeny Mishin. It was published back in 2017. His suggestion was that instead of current closure between region 2 and region 1 field aligned current system, current closure between the 2-loop substorm current wedge could be driving Saps. So I think there have been several studies that talk about finer structure inside the substorm current wedge. The traditional picture of having a single loop flowing in on the dawn side and coming out on the dusk side was, I think, challenged by many studies starting from early 1990s. And Evgeny Mishin's suggestion was that the current closure between such finer structures inside the substorm current wedge is actually driving Saps instead of the region 2 and 1 field aligned current system. So I think there have been a few observations that support the traditional paradigm, and there have been a few observations that support the newer paradigm. I'm going to talk about some of these in the next few slides. So that is a quick introduction to Saps. For those of you who are not familiar with SuperDAN, what is SuperDAN? SuperDAN stands for Super Dual Auroral Radar Network. Super is just included there because we're pretty cool. But anyways, it's an international network of high-frequency space weather radars. It's operated by several countries. It's a collaborative network. There's about 30-odd SuperDAN radars in the northern and the southern hemisphere. And the principal backscatter targets are decameter scale plasma irregularities in the F region of the ionosphere. We use a phased array to look into 16 to 24 beam directions, and we cover an azimuth of about 54 degrees. The typical range resolution is 45 kilometers, and we complete a single scan of 16 to 24 beams in about 1 to 2 minutes. The great thing about SuperDAN is that we produce identical data products that are routinely combined to produce hemispheric space weather maps. I think the most common product that you've encountered if you've used SuperDAN is the two-cell convection pattern, but there are several other byproducts, or actually, in fact, principal products that could be used in space weather research. So the picture on the right presents two SuperDAN radars that are located in Kansas, Fort Hays, Kansas. This is the main array. That's the larger one is the main array that's looking towards the west, and this is the main array that's looking towards the east. This is the Fort Hays East and the Fort Hays West radars. The array towards the back is the interferometer array. So the original superdawn chain was mostly centered above 60 degrees magnetic latitude, and the main motivation for moving to mid latitudes was that while the superdawn radars at 60 degrees magnetic latitude, or making measurements above 60 degrees magnetic latitude, were providing really useful insights into plasma convection or two-cell plasma convection during geomagnetic storms or during intervals of strong geomagnetic activity when the aurora level is expanded. Superdawn radars could not provide a complete picture of, or could not make measurements of the complete two-cell convection pattern. So back in the early 2000s, it was proposed that there is a necessity to develop superdawn or expand superdawn network towards the mid-latitudes. And this provides some sort of an incomplete picture of the current superdawn mid-latitude or the current superdawn network in the northern hemisphere. I chose this picture because this highlights the radars that were used in the studies that I'm going to present in the next few slides. Basically, the initial chain was centered above 60 degrees magnetic latitude, and starting from 2005, the first US mid-latitude superdawn radar was built in Wallops Island in Virginia, and then by 2011, most of the other US superdawn radars were constructed. Between 2011 and 2015, around 8 superdawn radars were operational, starting from Wallops Island radar in Virginia and expanding all the way into the Alaskan sector. The ADAC East and ADAC West radars were located in the ADAC Islands in Alaska. In addition, there are other mid-latitude superdawn radars. 2 of them are located in Hokkaido. Again, like I said, this is not the most recent picture, but there's, I think, 1 or 2 radars operational in the Asian sector by our Chinese colleagues, and they are rapidly expanding to provide more coverage in the Asian sector. I think 6 or 8 more superdawn radars are being constructed, or there's plan to expand the superdawn chain into the Asian sector by some of our Chinese colleagues. But basically, my study is focused around the US mid-latitude superdawn radars, and I'm going to use data from 6 to 8 mid-latitude superdawn radars. And as you can see, a significant advantage of these radars is that they're ideally located to make measurements between 50 and 70 degrees magnetic latitude, and that's the typical location of Saps as observed by DMSP and other DMSP satellites and Millstone Hill ISR. This is an example of what superdawn radars see, or the mid-latitude superdawn radars see. There are 3 different set of backscatter here, and what I'm presenting is line-of-sight velocities. These are not the 2-dimensional resolved velocities. The midnight meridian is shown here. These are data from the Christmas Valley East and West radars operated by our colleagues at Dartmouth College. And the most poleward backscatter that you see is coming from the two-cell convection. And if you move a little equatorward, centered around the 60 degrees magnetic latitude, you see a narrow channel of flows. The blue color indicates positive line of sight velocities, which is directed towards the radar. So an eastward-looking radar is measuring velocities that is towards the radar, and the westward-looking radar is measuring negative line-of-sight velocities directed away from the radar. So this is consistent with general flow direction, which is westwards. So in summary, these 2 radars are making high velocity, more than exceeding 1 kilometer per second measurements of plasma flows in the Sub Auroral Ionosphere that are directed westwards, pretty much consistent with Saps. This is what a typical Saps channel looks like in superdawn observations. And if you move further equatorward, we also make measurements of subauroral scatter, which is usually observed during quiet times, and there have been a few studies that have discussed this. These are typically of much lower velocities compared to what you see in Saps flows. So that concludes my introduction to superdawn and Saps. I'm now going to discuss some of the Saps occurrence statistics, how Saps location and velocities vary with magnetic latitude and MLT in the next few slides. And I'm also going to discuss an empirical model that we've developed of Saps using observations from superdawn radars. So I'm going to take another example of Saps flows now. Instead of just showing 2 radars, I'm going to show westward flow observed in 6 radars simultaneously. This is from an event that occurred on June 12th, 2018. And as you can see, the measurements are, so this is a view from looking down towards the Earth in the Northern Hemisphere. This is the North American sector. There are multiple data sets that are overlaid here, but the colored dots that are shown in this plot are indicative of superdawn measurements. And the flows are directed westwards, and the flows span about 6 hours in MLT. I think 6 mid-latitude superdawn radars were contributing to these measurements. And the colored dots that you see in this are representative of post-satellite total energy flux data. And the dotted circle, dashed dot circle here is representative of the best estimate location of the equatorward boundary of the auroral oval using post-satellite data. So clearly the flows observed in superdawn are, a majority of the flows observed in superdawn are clearly equatorward of the auroral oval determined by the post-satellite. And this is further confirmed by DMSP ion drift meter data. You can see 2 sections of flows in the DMSP data. One is located below the auroral oval. It is also consistent with what we see in the colored vectors represented by superdawn. And poleward of the auroral oval, you see a two-cell convection pattern, westward directed flows that is consistent with the two-cell convection pattern in the region. So one thing that this figure clearly demonstrates is the utility of using superdawn and how it provides a different context compared to some of the previous measurements. While DMSP is great at providing information about the finer scales along a certain longitudinal cut, the data provided by superdawn is useful in providing a broader context to the SAPS flows. SAPS flows in this case are observed across six hours in MLT, and there is a strong variability with MLT in these SAPS flows. So superdawn would be particularly useful in examining features, large-scale features of SAPS. And by large scale, I mean longitudinally extended features of SAPS. So now the question was, how often do we see SAPS? And to answer this question, we developed a statistical database of SAPS events using measurements from 2011 and 2015. And one of the key aspects of superdawn is that we operate continuously, unlike maybe say ISR, which is switched on and off during certain intervals of time. So this provides us an opportunity to see and examine if SAPS are being just observed during geomagnetically disturbed conditions, or if they are observed even during geomagnetically quiet conditions, and help us answer some of the questions that that remain about SAPS drivers. So what we did is we collected data between 2011 and 15 from several, from actually 6 to 8 superdawn radars that have been operational on the night side during this period, and divided this and used post-satellite data to identify flows that are equatorward and that are directed in the westward direction, which is consistent with what we call as SAPS. And we divided these data into different DST index spins representative of geomagnetic activity levels. So the lowest activity level is represented by the -10 to +10 DST index spin. And as the geomagnetic activity increases and we see strong geomagnetic storms, the DST level is expected to drop below 100 nanotesla. So this is indicated by the bin between -75 and -150 nanotesla. So in this case, we are presenting percentage occurrence of SAPS events in superdawn, and the numbers on the top indicate the number of hours superdawn was operational under these geomagnetic conditions on the night side, and the number of hours we actually make observations of SAPS. So it's not surprising. It's been shown before by several other studies that if there is a strong geomagnetic activity, you would very likely see a SAPS event. So, if you turn on superdawn radars if superdawn radars were operational during strong geomagnetic activities, especially during severe geomagnetic substorms or geomagnetic storms, there is more than 80% chance that you would see a SAPS flow on the night side. What's more interesting is that we were observing SAPS flows even during really quiet conditions. when DST index was between -10 and +10 nanotesla, we were still seeing SAPS for about 17% of the time. And when DST was between was above -25 nanotesla, we were seeing SAPS for about 32 or 33% of the times. So this SAPS observations during relatively quiet, or actually pretty quiet geomagnetic conditions, were a little surprising to us. And in summary, if you switched on a super-dawn radar, there's about 30% probability. If you combine all these statistics and randomly pick a night, there is about a 27 to 30% probability that you would see SAPS on the night side. So the next thing we did was develop a characterization of the location of SAPS flows. Previously, I was talking about the probability of seeing SAPS under a given geomagnetic activity level. So now, if SAPS are being observed by super-dawn, what's the most likely location of seeing SAPS for a given DST index bin? And that is represented in this plot. Again, we are moving from the lowest geomagnetic activity level on the top left side, and as we move down, we are moving towards strong geomagnetic storms, which are indicated by the DST bin between -150 and -75 nanotesla. Clearly, you can see that the highest probability of seeing SAPS, again, given SAPS is occurring, where is the highest probability of seeing SAPS in this DST bin? That's centered above 60 degrees magnetic latitude, closer towards the midnight, 22 and 23 MLT. And one thing that's more evident in this plot is that can be observed in this plot is that as geomagnetic activity level increases, the most likely location of seeing SAPS turns more equatorward and rotates more duskward. Actually, that feature becomes even more evident when we make a plot of mean SAPS latitude versus MLT, and that is what is being shown in this slide. The dots here are mean SAPS latitude, and these are color-coded by different DST bin levels. Red indicating the strongest geomagnetic activity level, and blue indicating relatively quiet conditions. And the error bars indicate standard deviations in the location, latitude and location with respect to that MLT. And the duskward and the equatorward motion of SAPS flows is much more evident in this plot. It's really clear to observe here. The equatorward motion of SAPS flows can be explained because the auroral oval is expanding during disturbed geomagnetic conditions. So the Sub Auroral location is moving further and further equatorwards during strong geomagnetic activities. And the duskward motion is likely because during strong geomagnetic storms, the asymmetric ring current, which predominantly is expected to drive the region 2 field aligned currents, is moving more and more duskwards. So perhaps that is the reason why we are seeing a duskward motion of SAPS flows during strong geomagnetic activity. So one of the things that we set out to do was figure out if we can model the location of SAPS using geomagnetic activity level as specified by DST index. So basically, our goal was to see if we can predict the location of SAPS given a certain geomagnetic activity level. And it turned out it was a very simple task to do. We could just model it as a two-dimensional Gaussian function, one of the dimensions being MLT and the other being latitude. The top plot is basically the actual probabilities of observing SAPS in the 50 to -25 nanotesla DST bin. I'm just choosing one bin here. And the second plot is the predicted probability by our model for this bin. This is basically a two-dimensional Gaussian representation centered around MLT and latitude. And the third plot is probability difference, or the error in our model. As you can notice, there's very little error, and it turns out it's a very simple problem to model the SAPS location using empirical functions. It's a two-dimensional Gaussian distribution in latitude and MLT. So the next thing we set out to do was validate the model. While we did some statistical validation of the model, this figure shows how the model varies under different geomagnetic conditions. I'm choosing two extreme cases. In the first case, I'm picking an event from 2015. Again, this was not included in the modeling. This was from a completely different test data set. Here, DST index was about -3 nanotesla during the time of the observation. The contours here represent the predicted model probabilities of identifying SAPs at this given location, at a given location, assuming that SAPs is actually occurring there. And these are DMSP satellite electron energy fluxes, and the dashed circle is indicative of the equatorward boundary of the auroral oval. And you can see that our estimate of SAP's location is in pretty good agreement with what SuperDAwn is actually observing. So the vectors here indicate SAP's observations in SuperDAwn data. And on the right side, I'm taking the famous 2013 St. Patrick's Day storm. This is around 20 UT. So things were so expanded during this storm that SuperDAwn was making observations of auroral flows. We were not making any observations of SAPS flows during this event. So I picked data from DMSP satellites. So you can see two different data sets from DMSP satellites overlaid here. The first is electron energy flux, and the second is drift meter data. And the contours here are also predictions of our model indicating the likely location of SAPS. And again, all the three DMSP satellites, F16, 17, and 18, are making observations of SAPS at this time, and they are in pretty good agreement with what we predict would be the likely location of SAPS. So that completes the location part of SAPS and SuperDAwn radars. We'll now turn into understanding the dynamics of the velocities. So I choose a different index here for determining the velocities. I'm choosing SMH index. The reason being SMH is more indicative of what's going on, or at least it is expected to be more indicative of what's going on in the asymmetric component of the ring current, and thereby more representative of region 2 field aligned currents, since region 2 field aligned currents were expected to drive SAPS. So again, there are four different SMH index pins here. The lowest one is indicated by 0 to 30 nanotesla, and increasing geomagnetic activity is indicated by the highest level of geomagnetic activity is indicated by the 90 to 180 nanotesla bin. The color bar indicates SAP speeds, and we are presenting SAP speeds for each of these pins as a function of magnetic latitude and MLT indicated by the y and x axis. So not surprisingly, you would see that SAP's magnitude increases with geomagnetic activity level, and you'll also start noticing some consistency with some pattern with MLT. So stronger velocities are usually observed on the dusk side for the strongest geomagnetic activity level. And typically during quiet geomagnetic conditions, we were seeing flows as low as about 100 to 200 meters per second. And as geomagnetic activity picked up, we were seeing SAPS flows that exceed 1500 meters per second. So I'm taking the magnitude aspect of the SAPS plot from, so previously I just presented the median SAPS velocities. In this case, I'm going to present the distribution of SAPS velocities using box plots in this case. So different colors are indicative of different SMH index pins, and red indicates higher geomagnetic activity, blue indicates the lowest geomagnetic activity level. I'm presenting SAP speeds versus MLT in this case. The box plot is indicative of the median, 25th percentile, and the 75th percentile distribution of SAP's velocities. So again, consistent with what we've seen in the previous slide, SAP's velocities are higher during when there is a significant increase in geomagnetic activity. But in addition, we also can see that SAP's velocities are higher in the dusk sector. Usually, sometimes they exceed almost 1500 meters per second during the highest level of geomagnetic activity. So these are the two patterns that we see with SAP's magnitudes. So how about the direction of SAP's velocities? So this is again presenting SAP's azimuth versus MLT for 4 different DST index bins. Here, minus 90 degrees indicates velocities are perfectly westwards, and increasing azimuths indicate flows that have an increasingly poleward component to them. And or in other words, if there is a higher slope, that means SAP's flows are increasingly polewards. or turning polewards as you move towards the dusk sector. And you can see that feature is much more consistent with disturbed geomagnetic activity levels. And SAPS flows have a significant poleward component on the dusk side. I think that is more consistent with the expectations that these flows eventually merge into the two-cell convection pattern or the high latitude convection pattern on the dusk side. So that probably explains why there is a higher poleward component to SAPS flows that we see. And we use a method called L-shell fitting to determine the direction of SAPS flows from the superdown radars. So another thing that we did was calculate SAPS potentials by converting the velocities into electric fields and then using the width of the SAPS flows to determine the potential drop across the SAPS channel. This is again showing 4 different DST bins, and this is an MLAT MLT map. Midnight is towards the bottom of the plot and noon is towards the top of the plot. So we find that there's about the SAPS potentials show a significant variability, but they're strongly dependent on geomagnetic activity. Usually you find SAPS potentials varying between 5 and 50 kilovolts depending on geomagnetic condition, and that's a significant potential drop in the Sub Auroral Ionosphere, and that clearly shows how much of an impact SAPS channel can have on the Sub Auroral electrodynamics. It can impact several other features that are observed in the Sub Auroral Ionosphere. We developed a model of SAPS potential. I'm not going to talk about the model here, but we also have a SAPS potential model that is developed using these observations. So the key points from this quick statistical analysis is that we find SAPS during a broad set of geomagnetic activity level. SAPS tend to occur about 15% of the time, but are localized to the midnight sector just above 60 degrees magnetic latitude during quiet times. And speeds are usually between 100 and 300 meters per second when the geomagnetic disturbance level is low. But as geomagnetic activity increases, we see that there is a very high chance of seeing SAPS, and they systematically shift equatorward and duskward with increasing geomagnetic activity. And during geomagnetic storms, they're usually centered around 20 degrees magnetic latitude and below 60 degrees, 20 degrees MLT, 20 MLT and 60 degrees magnetic latitude. And you can see speeds exceeding 1.5 kilometers per second. And usually median SAPS potentials vary between 15 and 45 kilovolts. And they clearly demonstrate the significant influence they can have on the ionospheric electrodynamics in this region. Finally, we developed a few empirical models of SAPS occurrence, location, and potentials, and we think this could be particularly useful for studies focusing on theoretical simulations of SAPS, and we'd be very interested in hearing about theoretical models of SAPS and how we could be contributing to them, or how our data could be useful for theoretical models. So I'll move on to, we've looked at some of the statistics of SAPS occurrence, location, and velocities so far. I'll move on to an examination of different influences in driving SAPS using a single event analysis in this study. So I'm choosing a specific event that occurred on July 5th, 2011. And this occurred during the recovery phase of a minor geomagnetic storm. CIMH index and SIMH index are barely dropping below. CIMH index is barely dropping below minus 50 nanotesla. There was some indicative, some indication of substorm activity. AL index was dropping below minus 500. It's, I think, reaching around minus 700 nanotesla. So this presents observations from July 4th to July 5th, covering 2 days. The period of interest for me is during the recovery phase of the storm, where it is marked by some substorm activity. There is some increase in the SMH index, and SAPS were observed in the mid-latitude superdown radars during this interval. So I'm going to start with 04 UT on July 5th, and the plot presents 3 different data sets. The left-hand side of the plot presents super down velocities that are scaled between -600 and +600 meters per second. I'm just showing the formation of SAPS flows here, and the red and blue contours are showing ampere data, ampere field aligned currents that are provided by the Johns Hopkins University. And the right-hand side provides super down data overlaid with median filtered total electron content data provided by the Madrigal database. And the dashed lines here indicate fields of view of the super down radars that are making observations of SAPS. So I'm using 6 super down radars in this case study. And clearly you can see that as expected, SAPS are located inside the low density trough region. And interestingly, however, one thing that we see is that they're little equatorward of the region 2 field aligned current system. You would ideally expect them to be located with the field, region 2 field aligned current system, or the downward region 2 field aligned current system if they are consistent with the traditional paradigm. But again, it could be possible that there are very small scale currents in there and that are not being observed by Ampere. But this is just the formation of the SAPS channel. You can just barely see weaker SAPS flows forming inside the super down radars. And I'm moving 20 minutes forward now. I'm looking at 0420 UT. SAPS is more expanded. You can see stronger velocities exceeding 600 meters per second. And the field aligned current system is now much more developed. SAPS still are embedded inside the low density trough region indicated by the lighter colors in the GPS-TEC plot. Interestingly, however, you can see that some of the flows are located equatorward of the upward field aligned, upward region 2 field aligned current system. If the traditional paradigm was very accurate, I would expect these to be located, co-located with some section of region 2 field aligned current systems that are downward. But instead, we are seeing they are co-located with, or at least a part of it is co-located with upward region 2 field aligned current system. So I'll now move on to another time instance here, which is about 05 UT. It's a very intensified SAPS flow. I think these are line of sight velocities, and they were exceeding 800 meters per second, 700 meters per second. The flows are still embedded inside very well-defined mid-latitude trough, but only a section of the flows are co-located with the region 2 current, downward region 2 current system. The other section is co-located with the upward region 2 current system. Maybe it has got something to do with the substorm current wedge, and some section of the flows might be driven by current closure in region 2 currents, downward region 2 currents, and maybe some section is controlled by the dynamics of the substorm current wedge. But what's more interesting is that during the declining phase of geomagnetic activity, when the currents were receding, we still see, so the currents, this is about 0545 UT, which is 45 minutes later. All the currents in the, or most of the currents in the Ampere field aligned from the Ampere data set are receding. They have weakened, they've moved forwards. We still see very nice SAPS flow across 6 radars, and you still see significant velocities in there. And again, they're firmly embedded inside the trough. Even though field aligned currents are moving polewards, we still see that they're consistently located at the same location inside the trough. This is after 545, at around 545 UT. And now the last plot is about 615 UT. The activity has completely declined. The field aligned currents have completely receded. They're about 70, they're located, the peak of the currents is above 70 degrees magnetic latitude, a little above 70 degrees magnetic latitude. We still see SAPS flows, and they still are located inside the mid-latitude trough. So, and these are not low velocities. The line of sight velocities are greater than 300 meters per second in this case. So this shows that even though there is a significant variability in magnetospheric driver, even though they are receding, SAPS flows are still firmly embedded inside the mid-latitude trough. I'm not very sure what's happening here. Maybe there is a contribution from the ionosphere thermosphere system that's dominating towards the end of the geomagnetic storm that's taking. Maybe there is a role played by the winds. Maybe there are some finer scale structures that are observed here. But one thing that we noticed was this picture was not very consistent with the traditional paradigm of SAPS or our current understanding of SAPS. So I just showed a few time instances previously, so I'm now going to select 3 different MLTs, 19, 22, and 0 MLT. And the left plot is a kilogram representation of ampere field aligned currents. The vectors here show superdawn SAPS flows. The right part is TEC units, it's GPS TEC data alongside SAPS flows. So at 19 MLT, SAPS flows are co-located with region 2 current system. Even though some portion of the currents move polewards, they just stay there firmly embedded inside the trough without moving, without having any motion with respect to the region 2 current system. But they're more consistent with the traditional paradigm in this location. But at the later stage of the event, there is no response to SAPS flows for a change in the current system. At 22 and 0 MLTs, it's slightly different from what we've seen on the dusk side. SAPS flows are now co-located with an upward current system instead of the downward current system. And even though the current system moves forward towards the end of the indicating a decline in geomagnetic activity, there is no response in the SAPS flows. They're still firmly embedded inside the geomagnetic, in the mid-latitude trough. So we found that this was interesting because the response of the system to a change in magnetospheric driver was not significant. It's indicating that the ionosphere-thermosphere system is probably taking over in this case. So a few key points to summarize are that we presented superdawn observations of SAPS and compared them with the location and magnitude of field aligned currents and GPSTs, mid-latitude trough specified by GPSTEC. And the relation between upward and downward FSEs, field aligned currents to SAPS, depended on the MLTs. Towards the dusk side, SAPS flows were a little co-located with the downward region to field aligned currents. And on the night side or the midnight side, they were co-located with upward region to field aligned currents. And during the declining phase of the event, as the field aligned currents weakened and moved forward, SAPS flows weakened, but they remained pretty much fixed inside the trough, and they did not move forward with respect to in accordance with the field aligned current system. And taken together, we feel these are inconsistent with this traditional paradigm of SAPS observations, that SAPS flows are produced by ionospheric closure between parallel sheets of upward and downward field aligned currents. And ionosphere-thermosphere processes could be dominating towards the declining phase of geomagnetic activity, and they might be playing an important role in sustaining SAPS flows, if not driving them towards the end of this event. So that concludes this chapter. And the last chapter that I'm going to talk about is an examination of interhemispheric conjugacy in Sub Auroral Polarization stream. So like I mentioned before, superdawn radars make observations in both northern and the southern hemispheres. So they provide an excellent opportunity to examine interhemispheric conjugacy or examine the degree of magnetic conjugacy in features such as Sub Auroral Polarization stream. So I'm going to pick an event that occurred on August 4th, 2010. This was a geomagnetic storm. I'm presenting IMF solar wind velocity, ALAU index, and SIMH index for interval of 2 days, starting from August 3rd to August ending on August 5th. And you can see there's significant variability in IMF BZ and BY, but they typically varied between +10 and -10 nanotesla. Solar wind velocity was about 500 kilometers per second. There was significant auroral activity. AL index dropped below 1000 nanotesla, and SIMH index and SIMH index dropped below -100 and exceeded +100 nanotesla respectively. The period of interest is between 0 and 6 UT on August 4th, which is pretty much the peak of the geomagnetic storm there. This was characterized by a significant substorm activity. So I'm presenting fields of view of magnetically conjugate superdan radars. I'm just showing line of sight velocities observed in the superdan radars in this plot. The left-hand side is observations in the northern hemisphere near Virginia. These are observations from Blackstone and Wallops radar. The fields of view of the radars are indicated by solid field of solid lines. And another radar that you see here is the Falkland Islands radar that is originally located in the southern hemisphere near Argentina, and the field of view of the radar is projected into the northern hemisphere along magnetic field lines using the SIG&MCO models. And you can see that this field of view is magnetically conjugate with the Wallops Island and to a certain degree with the Blackstone superdan radar. So the observations in superdan radar here are shown, and these are consistent with westward directed flows. I'm not presenting any satellite data here, but these are below the auroral level, confirming that these are indeed Saps flows. And on the right, you're actually seeing observations from Falkland Islands radar at around the same time, and the fields of view of Blackstone and Wallops radar are projected into the southern hemisphere in this case. So you can see that in both the northern and the southern hemispheres, superdan radars are making simultaneous observations of Saps flows. I'll quickly point out a couple of differences. Flows are much stronger in the southern hemisphere, but much broader in the northern hemisphere here. I'll quickly move on to time series analysis in the interest of time here. This is between 0 and 6 UT on August 4th, 2010. There was significant geomagnetic activity. KP varied between 4 and 6. The bottom three panels show a single beam from superdan radar between 0 and 6 UT. The fourth panel from the top is Blackstone radar in the north. This is Wallops radar in the north, and you can see Saps flows are shown in this case. Again, they are broader in both in the northern hemisphere and in the southern hemisphere. Saps flows are shown in the Falkland Islands radar. They're much narrower, but the velocities are much stronger compared to what you see in the northern hemisphere. So if we determine the velocities and compare all these parameters between the northern and the southern hemispheres, so the red line here indicates velocities in the southern hemisphere, black indicates velocities in the northern hemisphere. Clearly, there's almost 2x difference in the velocities. Velocities in the south are much stronger compared to what you see in the southern hemisphere. And on the contrary, a major difference between the northern and the southern hemispheres is that the latitudinal widths of the Saps flows are much wider in the northern hemisphere compared to what you see in the southern hemisphere. So in contrast, if you combine these two, we can see that the potential drops are pretty much in line with each other. There are significant differences between the velocities and latitudinal widths, but they're compensating each other, and the potential drop across the Saps channel in the northern and the southern hemisphere is roughly similar in magnitude and almost exhibits a similar trend too. So again, the key takeaway from the study is that simultaneous observations of Saps flows can be enabled by superdan radars in both hemispheres that have magnetically conjugate fields of view. And interhemispheric comparison showed that there were significant differences between latitudinal widths and electric fields between the hemispheres, perhaps associated with seasonal differences in conductivity and other factors, such as magnetic field distortion or asymmetric driving of the field aligned currents. But the cross-Saps potentials were pretty much similar in both the hemispheres, not just in magnitudes, but also in temporal variations. And this greater consistency in terms of cross-Saps potentials were likely due to the compensating differences between velocities and the channel widths in both the hemispheres. So that concludes all the three chapters of my talk here. Basically, to summarize, we've been making longitudinally extended observations of Saps for more than a decade now. We have a database of Saps events that exceeds more than 3,000 hours. That's just when we analyze 3 to 4 years of data. We have many more hours of Saps observations in currently, and some of our observations indicated that the traditional paradigm of Saps might not always explain the observation, might not always explain all Saps events, and there is more to it than what we understand now. And sometimes interhemispheric comparison shows that even though there are differences that are probably driven by magnetic field distortions or seasonal differences, there is greater consistency, at least based off an event analysis in cross-SAPS potentials. So lastly, I'll stop with the acknowledgements slide here, and maybe if you have any questions, please ask me now.
Thank you, Bharat. Does anyone have any questions? Either raise your hand or you could type them into the chat and I can read them. So Dong has a question. Go ahead.
Okay, yeah, thank you, Bryce. Really nice talk, and also really nice to have you here. I actually have a few questions, but let me start with the first two. So in your first statistic results, you showed the occurrence rate dependence on DST index. I'm wondering if have you looked at or have you thought about the dependence of the occurrence rate with the DST time rate? So because the DST, the absolute value may be depend on the specific storm, but what about like in which phase you are more likely to observe SAPs?
Yeah, no, that definitely has an impact on it. I didn't get a chance to separate it out based on the phase of the storm. I didn't have a significant amount of, most of the statistics happened between 2011 and 14, and I think I've had a handful of storms in there. I didn't get a chance to separate it out, but that would be a very interesting study. And I think that also comes out in the later section of my study where SAPS flows were just staying embedded inside the trough, even though the storm was receding and DST and CMH indices were getting back to normal levels. So the statistics might be different in such a case.
Okay. Yeah, in another study, you showed the potential drop across the SAPS channel.
Mm-hmm.
Yeah, I wonder, have you also, well, actually, this was a related question for me this morning when I was talking about another topic. So have you thought about, have you looked at like how much this potential drop is relative to that cross-polar cap potential?
No, I did not look at that. Usually it's in the order of a few tens of actually, I don't recall it. I think we took a quick look at it, but it forms a significant part of the cross-polar cap potential. It's a noticeable amount of the cross-polar cap potential there. I can quickly check the numbers and come back to you later. I can email you the numbers later. I don't recall it off the top of my head.
Okay, sure.
Yeah.
Well, I have more questions, but I'd like to give other people a chance to ask, so I may wait. No? Or maybe I can continue.
Are there other questions? Okay, go ahead, Wenbin.
Yeah, you said you observed SAPs during quiet time.
Yes.
As we know, the quiet time convection pattern is really complicated, especially in busy northward case. How you sure that this is a sub-auroral flow and these SAPs?
So we used measurements from post-satellite to estimate the likely location of the auroral oval. And we made sure that most of these measurements are actually, all of these measurements are consistent below the auroral oval to confirm that they are from a SAPS channel. We also used L-shell fitting technique to make sure that the observations we are making are indeed directed westward or predominantly westwards. We use plus minus 15 degrees variation from the perfectly westward direction to determine they're from a SAPS flow. But they are actually coming from a SAPS channel in the Sub Auroral Ionosphere. But I think this is where, like I said, it gets a little complicated because some part of what I call SAPS is what my colleagues call SAIS or Subaraural Quiet Time Ionospheric Scatter. So it looks like there's some transfer from SAIS to SAPS there. it's really difficult to distinguish between both of them when you get to really, really low geomagnetic activity levels.
Okay, thanks. Then the follow-up is for all, because Subaru only observed the drift velocity. So in each of your cases here, listed here, you have a auroral precipitation information tool, so you know which sub-auroral or is auroral.
Yes, yes. Yeah, we've used post-satellite data to confirm that these are below auroral.
Okay.
Yeah.
Thank you.
Thank you.
May I have another question, if no one else?
Yes.
Yeah, I noticed in your statistical results, you only show the, for example, the plot for Saps magnetic latitude distribution with MLT, probably next slide, your next two slide.
Yeah.
Yeah, so you don't show any point before 17 or after 2. Does that mean you didn't find that in Cyclone data, or it's just a very negligible amount of events?
So there are two things. So for very disturbed cases, it's likely that some of these some of the Saps flows are going below our observational limit. So I'm not able to find anything below beyond that range of MLTs. So for example, these could be happening at a lower latitude than 52, or maybe the location of Saps flows is below 52 degrees or 54 degrees. And that's why I'm not able to make a significant amount of, collect a significant amount of data in that region. But towards the higher latitude side, I'm more or less fairly confident that we have coverage in that region. It is probably that they're merging with the high latitude flows as you move more and more towards dusk side, and it becomes a little difficult to distinguish between both these flows in that region. The confidence level is a little less for strong geomagnetic activities on the midnight side, but it gets a little better on the night side. But it's also likely that I'm just using 6 to 8 radars, and maybe if there is a really elongated Saps flow that's being observed by the Hokkaido radars, or maybe some of the newer Chinese radars, I might be missing those, and that might have some impact on the statistics that I show here. But overall, if you look at the probability, though, the likelihood keeps decreasing as you move more and more towards the dusk side. At the center, it's likely that there is some smaller probability coming in from this region, but the center is in the 20 MLT and 19 MLT region.
Thank you.
Looks like there are a few more questions or comments. Sam, you want to go ahead?
Yeah, I had a question about the Ampere field line currents and how you're observing Saps equatorward of them. And it's, yeah, this, I wasn't expecting this because I thought we had really nice observations of the field line currents being pretty much co-located with the Saps. So I was curious, how far are they separated? And what do you think's going on there?
Actually, I guess that's a question for the modeling community. Can someone help me explain this? But like you said, we've seen examples. So for example, the June 12th, 2018 event, this was I think this example, I don't show any Ampere field aligned current data. This is a very good explanation of the region 2 field aligned currents co-located with Saps events. But when we picked out a different event and a different phase of the storm, we just noticed that it's different. With respect to the location of field aligned currents, and also the upward field aligned current system was a bit surprising to us. Maybe this is more consistent with Dr. Mission's substorm current wedge theory on the night side, and maybe the traditional paradigm of region 2 currents more consistent on the dusk. But I honestly don't know what's going on here. Maybe it's the winds that are driving it, or maybe the trough is sustaining it.
Yeah, maybe the lag feature.
Yeah.
Where it was previously established somewhere else. But yeah, I thought that was interesting. Thanks.
Chen, do you want to go ahead?
Yeah, I have a couple of questions. One is regarding the Southern Hemisphere, Falkland Island data. You only have one radar there. How do you be sure that the quantity of the measurement, because the angle is a pretty steep angle there to measure the zonal drift? Another question is, you take into consideration of the seasonal changes between the northern and southern hemisphere. What time when you're taking this data?
So this was August. This event happened in August, so it's not like a great summer or winter event, but this was the best we could get. Actually, Falkland Islands radars were, at least at that point of time, were making a lot of measurements from ground scatter and not ionospheric. So this was one of the rare SAPS events that we could identify. And coming back to the aspect of the look direction of the radar, you are actually right. It's looking pretty poleward, and what we are seeing is a very zonal, or what we expect SAPS to be is a very zonal flow. We can be more, I don't have the plots here, but I have them in the paper that I discussed, that I showed before. But basically what we did is we analyzed the variation in the magnitude of the flows with the direction of the beam. There are, I think, 16 beams in here. And if there is any discrepancy or if there is any error in the measurement, I would not expect this. I would not expect a significant variability with respect to the look direction. So, for example, beams that are a little more zonal are seeing stronger velocities. The scale is a little saturated here, but beams that are more or less poleward are seeing lesser line of sight velocities. So, if you assume that the flow direction is constant in this narrow region and make a plot of the variability between beam direction and the magnitude of the flow, the variability can confirm that these are either westwards or not, giving you more confidence about the measurements. But we found that these are significantly westwards. I don't remember the azimuth off the top of my head, but I think it was around -80 or some degrees, which is pretty close to westward. But we are fairly confident that this is from a SAPS channel there. And in addition, I don't show the plot here, but there was a DMSP pass that was going on, that was co-located with the measurements in the Falkland Islands radar that again confirmed the magnitude of the flows were consistent with what we saw in the radar. Actually, I think those are presented in this paper. So there's two observations. It's not just super down. There's also DMSP observations that confirm the results that we showed here.
Thanks.
Are there any final questions for Bharat? If not, then thank you again for a nice presentation.
Thank you for giving me an opportunity to present. Really appreciate it, actually.